COVID-free. So I know we've had a number of students in quarantine, but right now I think there are, what was there on Wednesday? There were 30 some students who tested positive, and then, but I think it was a total of 100, I forget now, and they said it was 98, and I forget that whether that was additional students or total that are in quarantine. But Valparaiso shut down today because of a spike there, and I guess there was some discussion of that here. But they've decided to try and stick it out for the rest of the semester. We just have a week and a half left, but that could change at any time. So I guess there was a big uptick at universities due to, they believe it was due to Halloween parties and stuff like that. So, you know, here it's been athletics, and 2 sport teams I think are now quarantine. Is that women's volleyball, men's soccer or something? Is that the 2? And so, you know, I ask, well, are they still practicing? And, you know, if they are, should they be? But apparently they're still practicing. It doesn't make any sense to me. It's like, well, you know, why don't we shut them down for the rest of the semester? But apparently that's not, you know, athletics is something else, I guess. So, right now, the plan is for next semester to open face-to-face still, but, you know, we've got this long break that's still 2 months away before we open up again. So things could definitely change by then. You know, COVID rates are going up. So someone had said that the Biden administration is considering actually shutting everything down for 4 weeks to try and get over this. Of course, they won't come into office until, you know, late January. So, you know, we could actually, I'm sure if they're saying they're going to do that, we will probably start online for a month in the spring semester. I'm hoping that doesn't happen, but, you know, just be aware of the fact that it might. Any questions about any of that? No, yeah, I've heard. Yeah, that I was listening to something on the radio this morning. They were saying, you know, they're out of the COVID war. You know, whatever COVID ward. You know, they've taken over the emergency room, beds in the emergency room with COVID patients. Beds in cardiac care are full with COVID patients now. So they're kind of at capacity. It has been recommended that students get tested before going home for Thanksgiving too, especially if you've got relatives you care about. You know, if you have relatives you don't care about, no, I'm not. But especially, you know, if you're going to be visiting it's probably best. I know your grandparents are not going to like this, but I would say stay away from your grandparents. You wouldn't want to live with the consequences of that. So hopefully we'll be over this in a few months with a vaccine available. But just be careful until. I don't know that it sounds as if, you know, this vaccine might not be available until probably late March, early April. So we'll be through most of the spring semester by then, unfortunately. So I'm not sure it will arrive in time for us for it to do much good for us in the spring semester. Okay. So I want to look at, we'll look at actually phase shift keying today, okay, and then frequency shift keying next time. So this is a technique for transmitting digital data wirelessly, okay. And we'll first look at the binary case. So this is called binary phase shift keying, or BPSK. Okay. And so we could switch between any two phase angles, okay. But typically, and for best performance, you want the two phase angles to be as far apart as possible. Okay, so let's just say we're going to transmit that for a binary 1 and 2 EB over TB plus pi, or 180 degrees for a binary 0. So now this is different than amplitude shift keying. Right? With amplitude shift keying, we were transmitting during 1 bit for a 1 bit and not transmitting, shutting our transmitter off for a 0 bit, or essentially switching between the two. Now, I will say that, you know, you could transmit amplitude shift keying between any two amplitude levels. So you're, but you'd have to add a DC offset, just if you're going to use envelope detection, just like we did for AM radio. Okay. Note here that a phase shift of pi is actually just an inversion. Okay. So is the same as just transmitting the negative. Okay. So with this, the energy per bit is constant. It's the same for both a 1 and 0 bit. Okay. And so the average is here equal to the bit energy, because you're transmitting the same energy for both a 0 and 1. We'll talk about reception. If you'll notice here, the envelope is constant. Okay. So envelope detection won't work. Okay, so we have to use a coherent receiver. But let's look at the generator is fairly straightforward. We'll look at that first. Okay. So we have an encoder from our ones and zeros, a digital stream, into a line code of plus or minus 1. But now, you know, if it's a plus 1 for a 1 and a minus 1 for a 0, then we've got our BPSK, okay. S of T. BPSK generator. The BT is polar NRZ, non-return to 0. So remember what all that means. So it's just going between two plus or minus levels for the full bit interval with an amplitude of plus or minus square root of EB. So when you multiply that, you get the square root of 2EB over TB. Okay. Again, envelope detection won't work. You have to use a coherent receiver. So with the incoming waveform, I'm going to show it as S of T2, but of course it would be transmitted over your medium, you know, additive noise, and then we have to multiply by a sinusoid at the same frequency and phase. So it's the same issue here with digital reception as with analog reception. There's a question about how do you get the exact same frequency and phase at the receiver that was used at the transmitter. And again, there are a couple different ways to do that. Again, you can transmit a portion of the carrier, you know, a small impulse, and then use a phase lock loop to recover that. But then low pass filter now, and you can go through the math here that if you multiply this again, we know what we'll get. We'll get the 1/2, and then twice the frequency. So when we run that through a low pass filter, we'll get 1/2 BT, ignoring the half. We'll get out of this an approximation to our binary waveform, our polar binary waveform. And then so we sample that and compare. So at this point, B of t should be going between a positive and negative level. And compare. And then we get our approximation to our original binary stream. Okay. And the bandwidth of the low pass filter should be at least 1/TB. Again, the modulated waveform has a bandwidth of 2/TB, but the low pass waveform, the baseband message, has a bandwidth of 1/TB. So let's, and it's a random waveform. So he has some simulation results here to actually calculate the spectrum from simulated data. And so what's showing here are the results of the simulation and the jagged line. And then the solid curve is the theoretical spectrum for binary phase shift keying. Again, it's done at a very low frequency, but we can make some, come to some conclusions about what we're interested in is the bandwidth primarily here. Okay. And so in this first case, it's binary phase shift keying. The carrier frequency is 4 Hertz. So again, we notice the spectrum is centered around 4 Hertz. Again, that's probably not unexpected. The next picture, he just changes the carrier frequency, and we'll see it just shifts to 8 Hertz. And we'll find that the bandwidth is not a function of the carrier frequency. It actually stays the same. Okay. In this picture, the bit width is 1 second. Okay. Again, much wider than would be used in practice, but it leads to some conclusions about the bandwidth. So we can see here, it appears that the bandwidth, the null-to-null bandwidth, is 2 Hertz or 2 over the bit duration. Okay. So that's what we're really interested in. You know, if we're transmitting at 1 megabit per second, then the bit rate would be a microsecond. Okay. And the corresponding required bandwidth would be 2 over a microsecond or 2 megahertz bandwidth required for that. So a fairly wide bandwidth required at a high signaling rate. So this one, same pulse width, 1 second still, but just changing the carrier frequency. So same bandwidth of 2 Hertz, again, 2 over TB. So nothing unexpected there, just illustrating that the bandwidth is not a function actually of the carrier frequency, but of the pulse width. And then these two pictures are same carrier frequency, 8 Hertz, but actually changing the pulse width. So here showing a pulse duration of 1 second, showing that the null-to-null bandwidth is 2 hertz, 2 over TB. And in the next slide, it's a narrower pulse. It's half a second. Narrower in the time domain, shorter duration. So it's half a second. So again, we would expect a wider bandwidth. And here, if you'll notice, he's changed the scale, but you'll notice that the null-to-null bandwidth is actually now 4 hertz, still 2 over TB though. So I think that's all I wanted to talk about. Yep, I haven't talked about this yet. So some conclusions based on the simulation that we have. About the spectrum. It's similar to binary amplitude shift keying. It is symmetric about the carrier frequency. Okay. And the transmission bandwidth is 2 over the pulse width. Okay. There is one, difference with amplitude shift keying. If you remember amplitude shift keying on the spectrum, we had an impulse at the carrier frequency. That's not present here. Okay. A really popular variation of binary phase shift keying or phase shift keying is quadrature phase shift keying. Okay. And it's a Fourier method using 4 phase angles. Okay. And they're typically 90 degrees apart, as you might expect. Okay. So we can write the transmission for any one symbol. So there's 4 symbols here. Now my notation's a little bit different. I've got an E here instead of an EB, and I'm using T here instead of TB. Because now every one of my symbols, S, these are subscripts I, I've got 4 of these. Okay. So each one of these actually represents 2 bits. Okay. So each symbol represents 2 bits. So the saving here is that, remember, our bandwidth appears to be inversely proportional to our pulse width. Okay. Here I'm using wider pulses, but I've got 2 bits of information embedded in each pulse, right? There's 4 possible symbols now instead of 2. They each have a different phase angle, but each one of these 4 symbols, it's twice as long as it would be if I were using binary phase shift keying. So the hope is the required transmission bandwidth will be half of what I would need for binary phase shift keying to achieve the same binary rate. Okay. So what that means is, and this, my notation now is T is the symbol duration. So TB is T over 2. And it means my binary rate would be 2 times my baud rate. It's when you get into M-ary signaling, a lot of people will use baud rate and bit rate interchangeably, but they're not really, okay? Baud rate is the rate at which I'm changing symbols. Okay. And then the bit rate is my effective binary transmission rate. So the bit rate will usually be, 2, 4, 8, 16, 32, 64 times the symbol rate. Okay. Now here I'm showing 4 different phase angles, but this has been extended in some cases, not only with different phase angles, multiple phase angles, maybe 8 different phase angles, but also 8 different amplitudes to have essentially 64 different symbols that are transmitted. Okay. And with 64 symbols, that's 6 bits at a time and a single pulse. Now again, it requires a lot of power to maintain the same bit error rate. It's a much harder problem trying to detect, which of 64 pulses, or it's even been extended to as much as 256 different symbols, amplitudes, and phases. So I'm transmitting an entire byte of information in a single pulse. But detecting between 256 different things or 64 different things, that is a lot harder than detecting between 2 things. Okay. So either I have to, usually requires a lot more power to maintain the same binary error rate. But there are some tricks we can play with gray level encoding so that if I misidentify a pulse, it doesn't necessarily mean all the bits in that pulse are wrong. So E is my symbol energy now. Again, for an apples to apples comparison, I want to make sure that I'm keeping the same bit energy for all the different modulation techniques that I look at. So last thing here is what we'll look at is the case where the phase angles are 45 degrees. What is this? 135 degrees. And then 90 degrees beyond that, 5 pi over 4. And then another pi over 2 or 90 degrees above that. Okay. For I between 1 and 4 then defines my 4 different pulses. And in phasor notation, the SI, and this is a capital S, remember in phasor notation I use the amplitude and then the phase angle. And so if I plot the corresponding, which is just a complex number on a complex plane, these all have the same amplitude. Okay. The angle it makes with the real axis would be the corresponding phase angle for these 4 different symbols. Again, this is the corresponding length, but in this particular case, I've got the same amplitude. I'm just changing the phase angle for the 4 signals. So one possible assignment might be that when we transmit that pulse represents the bits, the pair 1, 0. This is S1. This would be S2. This one would be 0, 0. This one would be 0, 1. At S3. And this would be 1, 1. Okay. Now it seems like an odd assignment. Do you guys remember talking about, or did you talk about gray code assignment in 254 maybe? Do you remember the term? It's how you lay out actually a Carnot map, where as you go from one line to the next, you just change 1 bit. So instead of the standard binary count, 0, 0, 1, and then 2 would be 1, 0. But as you go from 0, 1 to 1, 0, you're actually flipping 2 bits. Okay. In a gray code assignment, it's just a rearrangement, and there are a number of ways to do this. But you got the same 4 bit patterns, but as I go from this case to this case, I'm just changing 1 bit. I'm flipping just 1 bit. Okay. And as I cycle around, I'm flipping just 1 bit to get back to the 0, 0. The advantage of a gray code assignment is if I misidentify a symbol here, I'm much more likely to mistake like an S1 as an S2 or an S4, the 2 symbols that are on either side of it, than misidentifying it as an S3. Okay. So what that means is if I miss an S1, you might think, well, if I miss an S1, both bits are going to be wrong. But that's not necessarily true with a gray code assignment. If I misidentify S1 as S4, I still got one of the bits right. Okay, so it doesn't necessarily mean, if you misidentify the symbol, it doesn't necessarily mean that you've made an error in all the bits that that symbol represents. And similarly, if I called it an S2, I still got the second bit right, okay, even though I'm wrong in the first bit. So it would only be in the, and this is the less likely error, it would only be in the case if I misidentified an S1 as an S3, that I have both bits wrong, okay. And one of the things with binary communications, we're never going to be off making some decision, you know, where we're out here somewhere. You know, we're always going to be deciding between these 4 symbols. Okay, there's only a finite set to choose from, as opposed for an analog, you know, that analog voltage could be anything. So because of that, the bit error rate is not necessarily actually, you know, directly related to the symbol error rate. It's a little more complex than that. Okay. By using, it's actually hard to build a transmitter that actually flips the phase angles like that, but by using a little trigonometry, we can come up with a different representation. SIFT can be written as 2E of t cosine of phi cosine of 2 pi fc of t minus square root of 2E of t sine of phi sine of 2 pi fc of t. This is just a standard trig identity for the cosine of a sum, okay, of 2 angles. So it can be expanded like this. Now, for any given cosine of phi here are always, you know, if this is, say this has a length of, well, cosine of phi 45 degrees, it's always going to be plus or minus 1 over the square root of 2. You know, cosine is plus 1 over the square root of 2 here and here, and minus 1 over square root of 2 there. And similarly for the sine, it's always plus or minus 1 over the square root of 2. And that's why actually these angles were chosen instead of 0, 90, 180, and 270. Okay. So we can come up with a, so essentially all we're doing on this representation is, you know, this is going to be 1 over square root of 2 times this. So it's either plus or minus this amplitude times the cosine, and then plus or minus, you know, this amplitude times the sine. So we can come up with a scheme for generating QPSK, is first you read in 2 bits, so you have a serial to parallel converter. So you read in 2 bits, and then the first bit comes out along this data stream, A1 of n, and then A2 of n. Okay. And then this gets in line encoded. Really, this is just 2 binary phase shift keying methods, but one is modulated with a cosine, the other with the sine. Okay, so remember for the binary phase shift keying, it was just this expression where we had plus or minus 1, and that's what's going on here. This is alternating between plus or minus 1. So on this upper one, we're multiplying by this square root of 2 over t cosine of 2 pi fc of t. Okay. And then the other one, same line encoding. The line encoding is nothing more, again, than polar nRZ. If A1 of n is 1, I'm going to put out a plus voltage. If it's 0, I put out a minus voltage. And the same down here. And then now I have a narrow band phase shifter, 90 degrees, negative 90 degrees to go from the cosine to the minus sign with a negative 90 degree phase shift. And then add these 2 together. Is that right? The cosine, if I shift it negative 90 degrees, yeah, that gives me the minus sign, right? And that gives me positive sign, so I need to subtract it. Yeah. Cosine delayed, shifted by 90 degrees. I'm having trouble visualizing. Cosine shifted by 90 degrees will give me the sine. So that's the sine, and so I need to subtract it to get that minus sign in there. Okay. So this is a QPSK generator. Okay, the trade-off here for what we'll see is this requires half the bandwidth as the binary phase shift key method, which means, well, it means that if I have a channel with a given bandwidth, I can get twice the binary transmission rate with QPSK than binary phase shift keying. So if my bandwidth is 1 megahertz, and then I get, so say 1 megabit per second using binary phase shift keying, and that same bandwidth channel, I can get 2 megabits per second using quadrature phase shift keying. And that's just a function that, or that's just due to the fact that the bandwidth is related to my pulse width. And my pulses are wider with M-ary signaling. Okay, the receiver has to be coherent. So, and you could probably come up with this based on the transmitter. This is my square root of 2 over t cosine of 2 pi fc of t. And then low pass filter. This would recover my A1 waveform, and this would recover my A2 line encoding, and then I sample each of these at a rate of IT, and then compare the threshold. And then now I need to shift both of these into a parallel to serial. To get out my B of n. So this is a quadrature phase shift key receiver. And so this is kind of showing, again, this is theory and simulation of quadrature phase shift keying, carrier frequency of 8 hertz. Now notice here he's listing actually the bit width. Okay, so each symbol consists of 2 bits. So the symbol width would actually be 2 seconds here. Okay. So we would expect the null to null bandwidth to be 2 over 2, okay, or a 1 hertz bandwidth. And that appears to be the case from 7.5 hertz to 8.5 hertz here. Okay. So if you compare this to the earlier case at 8 hertz, the same bit width, there we had a bandwidth of 2 hertz. Okay. But here, the pulse width is actually twice the bit width. And then this is showing the same actually now for 0.5 hertz, but I'm sorry, 0.5 second for the bit width. Because it's QPSK, the actual symbol width would be a full second, and the corresponding spectral width would be 2 over a second, or 2 hertz. So he talks about, although I don't think I'll get into the details of this, there's some undesirable properties of QPSK, because I can occasionally have, you know, case, I forget what I had these labeled, 0, 0, and maybe 1, 0 here. So if one pair is 0, 0, and the next pair is 1, 0, then there's a 180-degree angle phase change between consecutive pulses. That causes some undesirable amplitude variations. So there's a variant of this called OffsetQPSK, which I'm not going to go into the details of. It has the same spectral properties as QPSK. It just does, you never have a change of 180 degrees, because actually these are, the changes in these two channels are offset by a TB width instead of a change every T. So you never get more than a 90-degree phase change. But it has the same spectral properties. You can look in the book for details, but I'm not going to actually talk anymore about offset quadrature phase shift keying. Okay. I think that's it for today. So we'll look at the last of these methods, frequency shift keying, on Monday. So have a good weekend. Just don't have any fun.